Good morning. We will discuss further on the autorotation. In a normal powered flight, the direction of flight, the air is attacking the rotor from up. In autorotation, the air is attacking the rotor from down and we are generating energy from the wind. What is the condition of autorotation in helicopters? First, we have to have a quick descent. If you remember, the rate of descent of a helicopter C must be higher than twice the induced velocity at the level of the rotor. Taking a blade profile and representing the velocity distribution here, we will have in a pure vertical descent, the omega r, the velocity of the blade, and the velocity c plus vi directed upwards. You see that the lift vector is tilted forwards and we are actually generating a propulsive force in autorotation. In this way, we can keep the rotor RPM almost constant by just decreasing the collective, and we can generate energy from the rotor. It can be demonstrated that in vertical autorotation, the rate of descent has to be higher than twice the induced velocity at the level of the rotor in order to be able to generate lift. If you recall the total power in a blade element theory, it is the induced power kWvi, the profile drag power pp, and the climb power weight multiplied by c. This is zero as we are having an engine failure. In this way, just substituting this in the equation, we obtained that C plus Vi equals with minus Pp over W. Using non-dimensional notation and non-dimensionalizing by induced velocity in hover, recalling also that the ideal power is defined as the power to weight to lift a certain weight W, and recalling the figure of merit according to the blade element theory, one can obtain the relation given on the right hand side, namely that C plus Vi equals with minus 0.5 induced velocity in hover, which is equivalent with the rate of descent is twice induced velocity in hover. So it follows indeed that the descent speed in a vertical autorotation must be in the same order as the downwash velocity in a full developed wake, twice induced velocity of the hover. So that is between 20 and 40 knots. Why does the rotor still rotate and thus is developing lift force when the engine is not working? The explanation comes if you recall the way the lift is generated. You remember that at the level of the rotor, at the profile, if the angle of attack is small, the lift vector is tilted backwards, and actually the lift force is creating a drag force. It is a resistance force. If the angle of attack is large on the profile, the lift is actually tilted forwards and we are going to generate a propulsive force. It follows that in autorotation we need to generate propulsive force from the lift in order to keep the rotor rotating. Autorotation in helicopter, it is a kind of equilibrium between autorotative and anti-autorotative areas on the rotor. You remember that actually in a moderate descent flight, the air is passing upwards, is deflected towards the periphery, and then is passing back through it. If you look at two radius, R1 and R2, and because the R2 is higher than R1, the tip velocity omega R2 is higher than omega R1, and actually the angle of attack alpha 2 is smaller than angle of attack alpha 1. In autorotation we can divide the rotor in three areas, A, B and C. In area A, the angle of attack is very high, the omega r is very small, and actually the rotor is stalling. In region B, you see that alpha, the angle of attack, is still high, but the lift is directed forward. So we are generating propulsive forces. It is the so-called autorotative area. In region C, at the end of the rotor, the angle of attack is small, omega r is big, and it is called the anti-autorotative area, and we are generating resistant force from lift. All this in equilibrium will ensure that we have a constant RPM that we can autorotate. In autorotation the rotor is in equilibrium. So as I told you, it is region A with a resistant force, region B with a propulsive force, and region C with a, again, resistance force. An equilibrium where the effect of autorotative force is cancelled by the anti-rotative forces, and the rotor rotates at constant rotor speed. There is actually an automatic stabilization of RPM in autorotation. If the omega, the RPM of the rotor, is increasing, the angle of attack is decreasing and the anti-rotative area is increasing, reducing the RPM. If the omega is decreasing, the angle of attack is increasing and the anti-rotative area is increasing again the RPM. The collective and the rotor RPM in vertical autorotation have a certain speed for every condition that you apply to autorotation. Here you see for a helicopter the tip speed omega r as a function of the rate of descent and collective pitch. You see that for every tip speed we can achieve a certain collective speed and a certain rate of descent. So vertical autorotation is a stable condition where for one collective pitch value the helicopter will settle at one rotor speed and one rate of descent. This can be calculated for every given helicopter. In order to enter in autorotation, we have to perform the flare maneuver. Here you see the flare maneuver. Imagine that the engine has failed and our goal is to keep the RPM at a constant value as long as possible. The whole autorotation means managing the kinetic energy stored in the rotor. Point 1 is a point of normal flight. In point 2, the engine failure happens. At that point, the collective pitch must be full down, immediately drop the collective from two reasons. One, to reduce the power extracted from the rotor and thus save the rotor speed, and B, to get the helicopter into autorotation condition. Then At point 3, one has to hold the constant speed. Actually, we have to build up some forward speed and actually transform potential energy in kinetic energy. At the end, from point 4, we perform the flare maneuver to come down. First flare, we have to tilt the thrust back, and that has to be done by increasing the collective. In a cyclic flare, and then we have to pull forward the cyclic stick to stay horizontally. In point 5. In point 6, we have to apply the forward cyclic to level attitude, and then we have to increase collective to slow the rate of descent, and then go finally landing. The analogy can be made with a water system between autorotation and the water system. For example, if you consider the rotor RPM, the water level in a normal situation, the loss of water leaking out will be balanced by the water pumped in the engine. If the engine fails, two reserves can be used. Potential energy coming from the height above the ground and the kinetic energy coming from the forward speed. In order to know where we can auto-rotate and not, the deadman's curve is plotted for every helicopter. You see here the deadman's curve for the Huey helicopter. It is a representation of the altitude above terrain as a function of the indicated airspeed. The deadman's regions are the areas, the darker areas, where we know that no safe landing is possible in this area. There are 2 points defined here in the lower part. Point A is called the low hover point and point B the high hover point. Below point A, so below the low hover point, after an engine failure, the helicopter will touch the ground because the rate of descent is low enough and the helicopter will not damage. However, between point A and B, it is not possible to land vertically when we need to auto-rotate, and we need to accelerate forward in order to perform safely auto-rotation. To gain enough speed in order to go forward, we need to have a minimum altitude, and this is the high hover point. If an engine failures at this point, at zero forward speed, we have enough altitude in order to build forward speed and auto-rotate safely. There is another region in this area. It is on the right hand side and at high forward speed and low heights. In this area, the time available for the pilot to perform a safe landing is too small. The deadman's curve is changing as the helicopter weight is increasing and as the density altitude is changing. Namely, increasing the weight and the density altitude both will expand the unsafe region in the deadman's curve. As a rule of thumb, it is that a curve established at the sea level will expand as a balloon as we increase the weight. For example, increasing the weight by 20% and going to 10,000 feet, it will give an expansion of 1.6. How to decrease the deadman's curve? First, one solution is to have a greater disk loading. So the greater the disk loading, the higher the hover point. one can use a very high inertia rotor to reduce the deadman's curve. For example, the ramjet rotors could make a power-off landing and then take off, fly again for 100 yards and then land back. What are the control problems in autorotation? The most known problem is the vertical stabilizer ineffectiveness. You see here the dynamic pressure ratios at the BO-105 helicopter tail, vertical tail. And you see the helicopter in climbing flight, in level flight, and in descending flight. You see that in descending flight, the pressure ratios are very low. And actually, if the stabilizer is in the wake of the rotor, the dynamic pressure at the stabilizer in autorotation is half of that of the level flight. In this way, the vertical stabilizer becomes autorotation. Helicopters without tail rotors, as the tandem helicopter, the coaxial, a fenestron or a notar have a vertical stabilizer, and this is quite ineffective in autorotation. How to solve this problem? Here are some solutions. For example, the BK117 used end plates stabilizer. So at the end of the horizontal stabilizer, two plates have been put there to get the vertical surfaces in clean air into autorotation. Another solution is to place a vertical fin under the tail boom, and in this way the air is clean in this descent. This was done for the Eurocopter Super Puma. Sikorsky ABC, the coaxial helicopter, the advanced blade concept helicopter, it also had directional control problems. Here, the directional control were ineffective into autorotation. The solution put there was that the vertical stabilizer was swept back to increase its aerodynamic effectiveness. Some other problems of autorotation. It is the tail shake due to the unsteady airflow. If the frequency of the turbulence is matching one of the horizontal or vertical stabilizer natural frequency, we will find ourselves in a resonance situation. The coaxial rotors have also a problem because usually they may experience control reversal into autorotation when one is applying the so-called differential collective, which has the two rotors are put in rotation. And this course on autorotation.